Hello everyone, my name is Yang Song. I'm the PhD student at the Center of Architecture and Visual Arts (CAVA) in the School of Architecture, University of Liverpool. The research title that I'd like to present today is DigiComponet, Augmented Reality Real-Time Immersive Design and Robotic Fabrication Workflow for Parametric Architectural Structure. This research project entitled DigiComponet looks at the future possibility in the architecture and construction industry to achieve the real-time immersive design and digital fabrication workflow for parametric architectural structure through augmented reality AR environment and human-robot collaborative method. This research aims to define new ways for how designers create processes are linked to robotics in real time, using AR, immersive design, and man-machine collaborative fabrication process. DigiComponet project creates an experiment design prototype in which designers' gestures are being identified and recognized through AR in a real-time immersive design virtual environment. A fabrication prototype in which robotic operations are being controlled by humans through AR environment, and an assembly process in which traditional 2D drawings are replaced by 3D on-site holographic guidance for unskilled laborers to enhance the assembly efficiency and accuracy. DigiComponet project will show the research result of such AR assist test, for which I use an UR10 robotic arm and a Microsoft HoloLens, as well as in terms of software Rhino, HL Robotics, FU Robot, and Photogram plugin in Grasshopper. About the introduction, AR can produce a virtual model in real environment while making the virtual objects information to consist with the real world. It aims to bridge the gap between the virtual world and the real world. Over the past decades, the assembly of complex structure requires detailed 2D drawings and skilled labor to interpret and operate. This method costs time and compared with the drawings accurate construction by skilled labor. To reduce the gap between 2D graphic instructions and 3D assembly actions, the use of AR technology has been applied to visualize assembly operations. In deliberate method by using high precision and detailed AR 3D on-site holographic drawings in the architectural assembly and construction process. Direct hand-based gesture recognition and inputs are considered as a main trends and capabilities for AR interactions. AR design has the possibility to combine the interactive design inputs and intuitive 3D on-site design preview. The impact of this development will help allow the designers to present and evaluate the work in more intuitive and simpler way. Robotic fabrication is also an important part of digital construction process when the material is not suitable for manual handwork. The robotic operation process requires specific experts, computer science knowledge, and skilled programming code workers, which is not in line with the designers and the laborers allocate of architecture industry. The AR technology enables the user to visualize and interact with 3D holographic models easily through a simulation on mobile device or AR headset. It visualizes the property of AR makes robotic operation simpler and safer for intuitive visual simulation and provide a faster and intuitive robotic programming than conventional techniques. About the research methodology, this project departs and elaborates the concept of AR immersive design and fabrication workflow for parametric architectural structure, which can be effectively managed manually or robotic assisting by unskilled laborers according to the different behavior of material and holographic instructions. This research has the potential it can be applied to a full architectural scale, such as the facade construction and the manual unachievable material fabrication, which could provide a new workflow for human-robot collaboration through the AR environment. DigiComponet Test 1. Augmented Break Column. The Test 1 explored the possibility of AR immersive design and assembly process through an augmented environment with virtual information on handheld device. In Test 1, the research mainly studied different methods of AR immersive design inputs, such as the human gesture and mobile device input, and explored the 3D virtual instructions for unskilled laborers to use in manual assembly process, instead of translating traditional 2D drawings to the onset. For AR immersive design part, the DigiComponet Test 1 set up different parametric variable inputs that will affect the result of outcome in AR immersive design. Different from the traditional design method, this research will show the on-site basic break columns structures in AR environment and provide several interaction input parametric sliders for the designer to interact with during the AR immersive design process. The adjustable parameter sliders are divided into different parts which cover the entire design process, such as the break layer shape, the number of layers, column rotation degree, column deformation control line, and the pattern gap distance. These sliders are connecting with parametric in Grasshopper directly and showing in the hologram app interface on the mobile device screen in real time for designers to modify with. The outcome will be shown dynamically on the handheld device according to the real-time immersive inputs. After the shape is designed, it will be transformed to the PX simulation plugin in Grasshopper and preview in the AR environment for structure stably simulation for calculate for a stable shape. For AR virtual guidance assembly part, the DigiComponet Test 1 provides an unskilled laborer a step-by-step virtual guidance assembly instructions. After the shape of the break of column is designed, the user can switch the toggle from the interface from AR design to AR assembly. The user will first preview the number of the break to be used and will be guided to the place of each break and virtual model shown on the mobile device. Although the result of the Test 1 is quite successful, it has a massive limitations through this handheld device AR system. In this way, the designers can only import the parameters by adjusting the sliders using the limited actions on the mobile phone screen, such as on press, on drag, on hold, or on release. Moreover, the laborer needs to use one hand to hold the device and the other hand to carry the assembly process, which will bring the safety hazards and the operational inconvenience to constructions. The best solution is to find an AR device and a method to offer a 3D holographic fabrication introduction instead of using handheld device to improve the accuracy of physical outcomes. DigiComponet Test 2. Augmented Brick Wall. The Test 2 explored the possibility of AR immersive design and the assembly process in AR holographic guidance with hand mode displays (HMD). To solve the limitation of handheld device, the researcher decided to use an HMD device for improvements such as the Microsoft HoloLens. The Microsoft HoloLens was invented to show 3D holographic and animation overlaying in the real world, which can illustrate 3D fabrication guidance. It enabled the user to engage with the digital contents and interact with hologram in the real world. For AR immersive design part, the The research involves more intuitive immersive input method. Different from the immersive design test 1, the experiment will use the hand tracking, gesture recognizing, and device location recognizing method to give the designer more possibility and experiments of real AR immersive design through HoloLens. First, the Microsoft HoloLens can scan the surrounding space of on-site project location using the spatial mapping technology and transfer the OBJ 3D mesh to Grasshopper. The spatial map will be optimized and shown through an AR device. Second, the designer can draw the control line baseline of the brick wall in the on-site immersive AR environment by tap and drop the hand gesture or the mobile device screen. The user can live preview the on-site holographic shape and adjust the control baseline at any time in the AR immersive design. Last, the designer can adjust the wall shape by tap and hold the control point shown on the wall surface. After the shape is determined, the user can preview the brick wall as on-site holographic model in the AR headset and can adjust the number of the brick, the angle of the brick structure density, and the brick pattern arrangement by interacting with the AR sliders through real-time immersive design process. For the AR holographic assembly part, Test 2 provides the user with an intuitive immersive holographic assembly guidance through HoloLens. When the user wants to build the brick wall, they just need to switch the toggle from AR device, AR design to AR assembly to follow the right guideline, as same as the process in Test 1. Designers can just walk through the on-site holographic model and use hand gesture to operate the assembly process state. The main difference is that Test 2 is a hand-free workflow that gives user more flexible manipulations and a more immersive AR surrounding experiment. However, as the HoloLens sensor are affected by the surrounding environment and the light, the holographic model sometimes has a bit drift from the specific location, which needs to restart the device and scan the QR code to correct location for several times. So during the assembly process, the user needs to pay attention to the surroundings. Test 2 targets at the manual achievable material bricks. However, for the large-scale architectural construction projects, the material might be beyond the range of the manual achievable, such as the concrete brick, the large-scale wood, metal bricks, and so on. Developing an interactable robotic fabrication in the AR environment for man-machine collaborative workflow seems that the solution for constructible manual unachievable large-scale architectural materials. So for the digital component test 3, it is the augmented robotic fabrication. Test 3 used the brick as an example and studied the feasibility of robotic fabrication in AR environment for promoting this AR design and assembly workflow to manual unachievable material. Digital fabrication techniques, which are defined at the process of construction determined by the digital tool path through the user computer-controlled robotic machines, have provided the possibility to design and construction that it is very expensive or difficult to construct using the traditional fabrication method. The traditional robotic operation needs specific expert computer science knowledgeable and skilled programming code workers to plan the movement, which will be dangerous for user in physical when some errors occur beyond the simulation. AR provides an on-site holographic robotic trick simulation preview and interactive virtual robotic control method. For AR robotic fabrication part, we design a simple robotic fabrication operation, pick and place, so the user can preview the brick location in the material preparation area and the target location in the assembly area through HoloLens. After they place the physical brick in the preparation location, the user just needs to tap the holographic on the preparation brick and tap the target location in the assembly area. It will send the operation to the robotic arm from the HoloLens sensor to FU robot plugin in Grasshopper. The user can preview the whole holographic simulation through HoloLens and switch the toggle to operation to compare the whole manipulations. Test 3 provides that it is a safer, more efficiency method to operate robotic in AI environment with the on-set gestures command and holographic trajectory simulation. All computer science programming techniques has been coding in Grasshopper, so the user just needs to point the preparation location and the target location. The current function of DigiComponet in Test 3 is very limited. The material of the experiment is also limited to brick material because the technique issue and the equipment limitation, but this will be solved in the future. About the conclusion and further works. The DigiComponet prototype test gives an overview of current state of AR technologies such as AR immersive design, AR holographic assembly, and AR robot operation. This paper is also indicate the potential of these applications in the field of building elements and architecture scale design. In conclusion, the DigiComponet project tried to bridge the gap between the digital design and fabrication physical outcomes by designing a workflow that includes AR immersive design, AR holographic assembly, and AR robotic fabrication. Using this workflow, the AR device and computer can detect and identify the user thinking and idea at any time, transfer the gesture and recognition into digital outcomes calculated by the parametric rules in Grasshopper. Preview the holograms overlapping in the real world in real time through AR device, and get the physical outcomes either in the AR holographic assembly method or AR robotic fabrication method depend on the material behavior. It brings the possibility to interact with AR and get the humorous advantages of feedback through AI to designers in real time. And about the further work. The further work will take, in addition, developing and involve multiple AR participants to the whole workflow to reduce the tolerance due to the command transformations. Some sensors will be used to catch the capabilities of human gestures and in the immersive design parts. Multiple robotic arms and robotic operations will be developed for the man-machine collaborative fabrication part through AI environment. The final goal is to make the whole AR design and assembly workflow simply and modified for architectural scale elements and applications. And that's all. Thank you.